Welcome back, guys. This will be the last video for Unit 3. We're going to go back and review states of matter and phase changes. Once again, I know you've had this in your classes before, but like everything else so far, we're going to add a little bit more to it. So let's get started. Okay, states of matter, and hopefully I can zoom in on this when I edit this video, but let's start with the solids first. Molecules of a solid are very close together. That's how they stay to be a solid. You'll see, you can see the liquid, the molecules become close. Guess what happens when you get to the gas? Obviously, they can become far apart. But solids, if you just take a look at your pencil or your pen that you're using, they have a definite shape and a definite volume. That pen or pencil has the shape of a pen or pencil, and it has a set volume unless you sharpen it if it's a pencil. But they're very restricted in motion. They can rotate and vibrate only. That's all they can do. They can sit there and spin, or they can vibrate and buzz against each other. That's actually how the heat will transfer through a solid, is by that vibration, adding friction. They have high densities. Solids tend to sink. You know that. And they are not compressible hardly at all. So take a look at that pen or pencil that you're writing with. Try to squeeze it. It's not going to change hardly at all. You might break it, but you're not going to be able to compress it very much. They do not expand very much with increases in temperature. They do expand a little bit. That's what you see with concretes and houses. They expand just enough to cause a problem, or they contract just enough to cause a problem. And then the diffusion of a solid is so slow you can hardly notice it. We just kind of assume that it doesn't quite really exist with a solid because those molecules are not moving. They're just rotating and vibrating. But it does happen on a very, very small basis. Okay, now let's go to our middle column, liquids. The molecules become more and more spacious. Their molecules are close. They're still kind of touching, but they're not far apart yet. They're not completely alone yet. Liquids will take the volume of their container, but they have a definite volume. For instance, take your liter of water, get a water bottle, pour it into a cup. Your cup probably has a different shape than your water bottle, and the liquid will take the shape of whatever container it's in. You can pour it back and forth. It will keep on changing its shape. But the liter of water is still a liter of water. So if I put that liter of water into the bathtub, it will take the shape of my bathtub, but I've still only poured a liter of water into it. So they can change shape, they do not change their volume. They have limited freedom of motion, and since these are liquids, they do have a degree of fluidity. Obviously, they're fluids. They have a medium to high density. They're less than solids except for water. So sometimes they float, sometimes they sink. Depends on what solution it's in. They are somewhat compressible. So if you get a cup of water and you get a piston to go right around your cup, you can push that water down to a slightly lower volume. Well, you can compress that very slightly. And they do expand and contract with increases and decreases in temperature. You can see that with ice, but for a different reason. And they diffuse easily, but not as easy as gases. So typically when we talk about diffusion with liquids, but in chemistry, that's more of a biology topic, so we're not going to cover diffusion a whole lot in this class. Now finally, we get to the far right column in our gases, and we've seen how molecules are very close with solids. They get more and more spacious, so now our molecules are very far apart. They're not even touching at this point, they just sometimes randomly collide with each other. Now they also take the shape of their container, much like liquids, but something very unique to gases is that they take the volume of their container. Now that'll be weird. We'll play with this in lab and I'll show you what this means. But with liquids, you had a liter of water. It's going to be a liter of water if you pour it into a bathtub or a gallon jug or whatever. With gases, they tend to expand very rapidly. Because they're not confined to bonds with each other, they're not actually bonding. I can take a liter of gas, put it into a gallon oxygen tank, and it will become a gallon of gas. It just becomes less dilute, but those molecules will spread to the volume of their container. Now we just talked about the next one. They're free to move in all directions. That's why they can take the volume of their container and the shape of their container. They have very low densities. That's why you have fog on top of lakes, because gas is almost always going to float on top of everything. And they can be easily compressed into smaller volumes. That's why, like I said, it could take a liter of gas, put it into a gallon container. It will take up that container, but I can also take that gallon of gas and compress it very easily into a liter of gas. It's great fun. They're also highly expansive with increases in temperature. The higher the temperature, the faster the molecules move, and vice versa. And they obviously diffuse very easily and very quickly because of that freedom of movement and the high speeds that those are moving at. So do you need to memorize everything on this chart? The answer is yes. Memorize all these because these are, what do we got? 1, 2, 3, 4, 5, 6, 7, by 3. So 21 questions that we could ask you based on this. So it's worth memorizing, but most of the time you can just kind of figure it out. So pause it if you need to fill these in. I'll zoom back out of it, and we'll move on when you're done. Okay, so an example problem. Here we go. We're going to get a lot of these. So a student determined that the substance he was working with took the shape of its container. So shape of its container. So right now, if we put our three things up top, solid, liquid, gas, we know that solids do not take the shape of their container, so we can eliminate solids right off the bat. Molecules moved fast and were very far apart. Okay? Right now you should be kind of thinking gas, but you may still be borderline between gas and liquid. But then the final statement, he determined that the substance was easily compressed into a smaller container. That, without a doubt, shows you that it has to be a gas, even though you could have figured it out by the second statement. So here's your answer. The answer is gas. Okay, last page. All right, phase changes. This is the process of absorbing or releasing energy. By energy, we normally mean heat, is what I want you to think about when we're doing this. To change from one phase to another. Here are your phases. The phases are the boxes. Please don't confuse phases with the change. Okay. So you have different types of changes. They're right there for you. You should go ahead and copy those down. You need to know them by the picture, is how I would tell you to memorize them, but also by the definition. If you know the picture, you also know the definition. You can figure that out. But if we're going from a liquid to a vapor, so liquid to a vapor is called vaporization. If we're going from a vapor to a liquid, going backwards, that's condensation. If we're going from a liquid to a solid, so liquid to a solid, that's this way. That's the easy one, that's freezing. If we're going from, that was solid to a liquid. Get the next one. Solid to a liquid is melting. Sorry, I mixed those up. Then you got a liquid. Then you got a solid going directly to a vapor. These are the two that people tend to confuse. A solid going to a vapor is sublimation. And then from a vapor back to a solid, that's the deposition right there. So those are your major phase changes. We don't talk about plasma a whole heck of a lot. We talk about ionization and deionization later on in the year, but not in great detail. So we don't really worry about those. But if we're on down, you go right ahead. And then the last part. You'll notice that all the phase changes either require input or they release input. So we can classify each one of these phase changes as one of two ways. The first way we can do it is called exothermic. Here we go. Exothermic reaction is a process that releases heat. So you have exo with the EX and exits with the EX. Told you you're going to get to this pretty quickly. And this become bigger and bigger vocabulary terms as the year goes on. So if exothermic is releasing heat and heat is exiting, then endothermic must be the opposite. So endothermic, a process that takes in heat, so you have endo and heat enters. En, En, Ex, Ex. That should make it fairly simple. So which of the phase changes are exothermic? Which of these are releasing heat? Keep in mind, if you can make your brain switch like this, if they are releasing heat, then it's actually becoming colder because it's releasing that heat. So we can take our graph, our picture over here on this side. This is why I like to just memorize the graph itself. If we're going to point to all the ones that are becoming colder because they're releasing their heat. So if we're starting with gas, condensation to a liquid is colder. Liquid to a solid, freezing, is cold. And then gas to deposition is very cold. So those are your three that are exothermic. Now the other way is true. All the arrows that are pointing upwards will be taking in heat, which means they're becoming hotter. So sublimation has an arrow pointing up, vaporization is pointing up, and then melting is pointing up. That's why we drew it on a little triangle, so they're not flat. We have our up and down arrows, but if you do it flat, you can do left and right arrows. But I really think that memorizing this chart will keep you straight for any type of question you might come across. So that's it. You'll get a lot more practice with these in class. That's all we got for you.